All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're going to continue working on the auto clipper. And I've made some progress since yesterday. I made some progress off stream. I'm actually glad that I did this off stream because it gave me a pretty decent idea of how heavy the model is going to be on data that I'm giving it. In this case, the data is an audio wave file, and it is dude. Okay, distill small en is great. It's lovely. It's lightweight. It also has a bunch of customizations, a bunch of optimizations in it that that can that can make use of various different hardware features that your hardware might have. However, even if your hardware doesn't have that, and as in you're using older hardware, it can still go the slow route and it's still going to work. So that's one of the good things about it. What I did notice is that it does still require a certain amount of time to process the the data. So initially, I fed a 2.5 hour VOD into it, and that didn't really go so well. First of all, I noticed that it was using all four cores because I was using it on uh, one of my machines that has a quad core CPU. Give me a second. I need to open up my stream manager just so I can see my chat. Okay. So what was I saying? Yeah, I tried running it on my quad core CPU, and this is great because like it's using up all the cores, right? What I did notice is that because it's using up all the cores, my fans started to, or in this case, one fan, it started to get really loud because as the cores are being used at 100%, their temperature is gonna increase because they're gonna get hot, obviously. And so after a while of that going on, I was like, no, hold on. I need to stop this because I feel like this is going to be running at full speed and at full usage for a while, and I'm not really all that comfortable with it. So I was like, okay, let me try this because I've done this with the cargo build process, the Rust cargo build process, where I was able to reduce the number of cores that it was using. So I looked up how to do it in this case. Also, another thing I realized is that apparently pipeline requires some sort of backend if you're going to be if you're going to be using a bunch of like models and stuff. It requires some sort of backend, either a PyTorch backend or a TensorFlow backend or any other backend that's supported. Initially, I didn't realize this that Hugging Face transformers and pipeline actually it's more of a wrapper around around a bunch of other functionality. In fact, it's not just a wrapper, it's sort of an abstraction layer as well, I guess you can call it. I'm not sure what exactly to call it because this is one of those things where it becomes like a convenience method where you can pass in different types of arguments, and depending on the argument that you pass in, you'll have different sort of behavior. I'm not sure what exactly to call that, but yeah. Anyways, pipeline requires some sort of backend, which is not a problem because I just installed. Once I realized that, then I installed PyTorch, and it was working. Also, the model weights, distill small EN's weights were only around 300 MB, let's say 400 MB because it might have been 350 or something like that. I don't remember. But yeah, 300 to 400 MB for the model weights, and maybe some other like config files might be required, which aren't really that big. Other than that, the model is, I believe it's defined within Hugging Face transformers. So I don't need to worry about any of that. And the code was as simple as what you're seeing on the screen here. You just define the pipeline object, and then you call that object as a method, and you pass in the audio file, and also well, you pass in the audio file path, and then also pass in a chunk length. The chunk length thing, I'm not entirely sure if this actually helped, because it was mentioned that Distill Small has its own chunking algorithm. It was mentioned in the, like, okay, so this is the output from one of the previous sessions. It took a good, like, I don't know, 10 to 20 minutes to transcribe a 10-minute audio clip. No, 1 minute. Sorry, not even 10. Not even 10 minutes. A 1 minute audio clip took around 10 to 20 minutes to transcribe. One of the reasons for that, to be fair, is that I set num threads to 1. By default, it was set to 4, because PyTorch tries to use, as much of your resources as possible, which is great. That's awesome. But in my case, I wanted to kind of limit it, so that not all 4 cores are running at full 100%. There'll be 1 or 2 cores running at 100%, and then I'm expecting the OS or the kernel to kind of move the work around if the CPU, if that specific core or those specific cores get way too hot, then just to give those cores some rest, maybe the OS or the kernel is going to move that work around. I need to have a conversation with Gemini about that, to see if that actually does happen, because there are certain conditions that need to be met in order for that to be beneficial. But if the kernel slash OS, I'm just going to say OS, if the OS, if based on, the variables at hand, the OS determines that switching from one core to another, or switching this work that's currently going on from one core to another, is going to lead to some sort of performance loss, then maybe it might decide to not do that. It might just, yeah, maybe it might decide to not do that. It might just sorry, zoned out. Um, yeah, maybe it might decide to not do that, and it might just let the work keep going on that specific core. I forgot why I was mentioning this. Um, yeah, okay. So sorry, sorry, zoned out. Yeah. Um, num threads. I set num threads to 1, so it would only use 1 core. Something that I want to do now is I'm gonna slice the. Can I do it here? Yes, I can do it here. So here I'm gonna do 30-second slice or 1, and this is supposed to be actually not even okay. You know what? Yeah, we'll do 30 seconds, and then we'll do 10 seconds. Okay, that's done. And then we'll do 10 seconds, just so I have, something to do the transcription with fast. Right, now I'm going to open up Yahtzee here, 10 minute, 10 second, 30 seconds, yank, and let's open up a new tab. Okay. Um, Here, where am I supposed to go? Yeah, there. All right, that is our data. So now that we have our data, I'm gonna temporarily increase this to 4 cores, and my machine is probably gonna get a bit loud, but hopefully we can finish this before things get a little too heavy. Yeah, let's run this. Um, oh, something else I forgot about is that the Python process itself is also going to take a certain amount of memory, so I need to watch out for that. But yeah, if you can see, oh wait, does BTOP look like shit right now on stream? Yeah, the green is not showing up, but the reds are going to be showing up. Yeah, yeah, definitely. The red is very much visible, but like any of the green, you guys can't see it. It might appear as gray or something else. Um, yeah, let's see how long this takes. Also, there's some of the information that was telling me that the chunking thing that I mentioned, it might not be doing as much as I think it's doing. Oh, also, I'm noticing that. Oh, I was about to say that the Python process is not taking as much memory, but I'm seeing it steadily increasing. So yeah, it might actually be taking that much memory. Hold on. Yeah, okay. So, oh, good. Okay, it's done. Great. Awesome. And the transcript is here. Um, let's wrap this. Yeah, that's better. So this is 10 seconds worth of audio transcript. It doesn't get dem keys right. It either reads it as deem keys or damn keys in this case or whatever. But yeah, this is the transcript. My usual thing. All right, dude, we are live. What's up, guys? And so and so, so and so, so and so. Great, awesome. I can move to. Oh, actually, you guys can't see it. I just realized that. Yeah, this is the transcript. Now you guys can see the transcript. Um, Now I need to. There was a thing about timestamps. Where's the thing about timestamps? Where was it mentioned? In fact, timestamps was mentioned somewhere. Oh, this is the chunking thing. We should probably read this just so I get an understanding of this. However, it is worth keeping in mind that just still small en, it has its own chunking method. Though I'm kind of confused by this thing. Where was it? So okay, here just so I can highlight what the what this thing was. Okay, using chunk length s is very experimental with sec-to-sec models. The results will not necessarily be entirely accurate and will have caveats. Okay. Ignore this warning with pipeline. All right. To use Whisper for long form transcription, use rather the model's generate method directly as the model relies on its own chunking mechanism. Um, CF. Wait, hold on. I'm missing something here. Its own chunking mechanism. What? What does that say? I'm I'm a bit confused about what I'm looking at here. Anyways, Whisper original paper. Oh, maybe CF is supposed to mean something. Something to do with like, okay, check out so and so paper. Using custom force decoder IDs from generation config. This is deprecated in favor of the task and language flags slash config options. Okay, all right. Um, where do they mention? Because I think it was Gemini that was telling me about mentioning the timestamps flag. Okay, split validation. No, this is dataset. To transcribe a local audio file, simply pass so and so long form transcription. Okay. To enable chunking, pass the chunk length S parameter to the pipeline. For Distill Whisper, a chunk length of 15 seconds is optimal. Oh, another thing, actually, okay, I need to look into this batch size thing as well. I don't know, I don't know too much about the batch size thing and how it works in order to be able to use it efficiently. Um, where does it mention timestamps, dude? Additional speed and memory improvements. You can apply additional speed and memory improvements to Distill Whisper, which we cover in the following. Flash attention. We recommend using flash attention too if your GPU allows for it. To do so, okay, I'll look into that later when I'm actually doing GPU stuff. Torch scale product attention. If your GPU does not support flash attention, we recommend making use of better transformers to do so. Um, we recommend making use of better transformers. To do so, you first need to install Optimum. Okay. Running Distill Whisper in OpenAI Whisper. To use this model in the original Whisper format, first ensure you have the OpenAI Whisper. Okay, nope. Uh, that's not for me. Then there's Whisper CPP. Distill Whisper can be run from the Whisper CPP repository with the original sequential long form transcription algorithm in a provisional benchmark on so and so, so and so. Okay, all right. Is there anything more? Transformer JS. Okay, it can even run on that. There's something for Candle coming soon. Interesting. I should look into that. I should keep an eye out for that. I should also keep an eye out of words. I should also keep an eye out for this 8-bit and 4-bit quantization. Right. Model details. I did not look at any of this. I should have looked at this. Where does it mention? Oh, there's also this thing about TQDM for the sake of getting a progress bar. I should look into TQDM because it was mentioned by Gemini in order to be able to see a sort of progress bar. Because for this situation, Transformers doesn't really give a progress bar. But using TQDM, apparently you can set up a thing to give you a progress bar. Give me a second. There's something that I need to some things, in fact, that I need to close so that my system doesn't slow down. TQDM. TQDM is a popular Python library used to add fast, extensible, and smart progress bars to loops and iterables, helping users visualize the progress of time-consuming tasks with its name coming from the Arabic word for progress and the Spanish word for I love you so much. Okay, all right, that's great. Um, it works by simply wrapping an iterable like a range or list with TQDM, displaying real-time updates on completion percentage, elapsed slash estimated time, and iterations per second. I didn't know this was a thing, dude. Well, I mean, I had a bit of a conversation with Gemini yesterday, so I kind of knew it's a thing, but like, um, this is interesting. Though this is mentioning that it's for, wait, okay, let me install this. TQDM. I'm in here. Yeah, UV pip install TQDM. And once that's done, is it done? Okay, all right. Import TQDM. Okay, I guess it was either already installed or wait, let me try that again. I think it might have already been installed. All right, cool, great. Here's what we can do. For the sake of testing this out, we can do this. Oh, you know what? Let's get Gemini to give us a little crash course on TQDM. Give it a second while it opens up. And in the meantime, we can, what are we looking at here? Oh, sorry, zoned out. Okay. I'm commenting this out. I need to, all right, let the authentication go through. Okay, it is taking some time. Okay, we're good. All right, first let's set the model. Um, I mean, this is light enough. Like, we don't need the heavy version. Hey, I do Python coding. I recently learned about a library, or I should say module, called, actually it's a package in this case, right? Yeah, let's say a package. About a package called TQDM, which helps with creating progress bars. Teach me about this package. No right actions necessary. Just give me the info. Usually I would try to turn it into like a whole course surrounding the topic, but I feel like that's not necessary because I'm just looking for very basic information about this. In the meantime, you know what? Hold on. I should do some research on the difference between Gemini 2.5 Flash Lite, Gemini 2.5 Flash, and Gemini 2.5. I forgot what the other one was. Gemini 2.5 Flash versus Flash Lite. Gemini 2.5 Flash is a balanced, smart, fast model for user-facing apps, while Gemini 2.5 Flash Lite is is an even lighter, faster, ultra-low latency version focused on cost efficiency for simpler tasks, offering a significant cost saving, but with slightly less reasoning power than the standard Flash, though still outperforming older models. Okay, I should add another versus there. Versus Gemini. Oh, hold on. Did Gemini give the response here? Okay. Let's look at the list of models because there's only three models that are yeah, Pro. Versus Gemini 2.5 Pro. Okay, Gemini 2.5 Pro is the most powerful for complex tasks. Gemini 2.5 Flash offers a strong price/performance balance for large-scale tasks needing speed and thinking, while Gemini 2.5 Flash Lite is the cheapest, fastest, and most efficient. Wait, Flash. Okay, Pro is the most powerful for complex tasks. Flash offers a strong price/performance balance for large scale tasks needing speed and thinking, while Flash Lite is the cheapest, fastest, and most efficient, designed for high throughput, low latency needs like simple classification, serving as a cost effective upgrade to previous Flash models with dynamic reasoning control. The choice depends on prioritizing capability, balanced efficiency, or extreme cost savings/speed. I need to have a conversation with Gemini about this because I need to understand what exactly it's about. Well, okay, let me mention this. Okay, the kinds of results that I get are also very telling because I wouldn't be getting a response so small from Flash or even from Pro. Pro is going to go into like full detail with this thing. So I guess that's one of the what do you even call this? Like one of the attributes of it. That's one of the things that happens when you go with Flash Lite instead of Flash or Flash instead of Pro. But the thing is, in terms of getting free, give me a second. Okay, in terms of getting free stuff, free requests per minute, requests per day, tokens per minute, tokens per day, whatever. Pro gives you the least amount. Flash gives you slightly more amount, and Flashlight gives you even more amount because each of them is, well, one is more powerful than the other, and another is more powerful than the other. Right. Okay. I was reading this. The TQDM library in Python is designed to add fast, extensible progress bars to your loops and other iterable processes. It helps you visualize the progress bar, the progress of your operations in real time. The name TQDM is derived from, okay, you can typically use it by wrapping an iterable with TQDM, for example, so and so. I am really curious about this because, okay, I'd imagine when you make something iterable, you get to define certain methods, and so I think that's what's happening here. When we are iterating over something, internally there are some methods being called, right? For because for us it's as simple as hey, for I in range so and so, right? But then internally there are some methods being called that make this whole iteration kind of behavior possible. So I'm guessing they've customized that behavior. So they do the iteration, but then they also add in this extra logic for printing out the progress, which is genius actually. This will display a progress bar in your terminal as the loop executes. TQDM is highly customizable and can be used in various concepts, including scripts, Jupyter notebooks, and more. It is known for its simplicity and efficiency. Our for loops and iterations The only thing it is used for. By the way, guys, hold on. I need to show you guys this because I'm excited for this. Um, Yesterday when I was, wait, do I have any of the course pages open? I could probably close this. LLM course. So I'm gonna go to Hugging Face Learn. Actually, it might be in this list, right? Maybe it might because the words, the course isn't yet complete. I think it's this one. Robotics course. Um, is it this one? It's this one. Yes. LeRoBot. I didn't know that this thing existed, and this course actually isn't fully complete yet. They're actively working on the course. This library is actively being worked on. Hold on, let me. Is there there's definitely a link somewhere here for, like, okay, this is the syllabus, and as you can see here, more stuff is coming soon. Currently, what they have in the course is welcome to the robotics course, then the course introduction and classical robotics. Eventually, they're going to go into reinforcement learning, imitation learning, and foundation models. What are the prerequisites? Okay, hold on. We'll get to this. We'll read this. Um, just a second. I need to find a link to that library. There it is. So I'm going to open this up and show you guys. And because of this, I decided to not go with the deep RL course and instead go directly to the robotics course, because that's kind of why I was doing the deep RL course to begin with. My main aim was to go towards robotics, uh, regardless of where deep RL was gonna lead me. My main aim was to eventually divert it towards robotics. So this is the LeRoBot library, and this, as you can see, very actively being developed. And this is a Python library, I believe. Yes. And I'm excited for this, dude. I'm I have, like, dude, I'm so excited to learn about robotics through this course. I'm actually considering starting doing this on stream. I have no idea if I'm going to be able to do it because, like, okay, they mentioned that even if you don't have the hardware, you can still simulate stuff. I do have hardware, but I don't think it's in. How do I say this? I don't know exactly what I need to simulate what they are teaching. So I'm first going to have to get an understanding of that. And then what I can do is I can first use their simulations slash simulators to simulate whatever they are teaching. And then I can try to apply that to ESP32. Because on the ESP32 side, I'm not going to be using this library. I'm going to be using something Rust based. So I need to find a way to apply the knowledge that I'm learning here to ESP32. Now, it could be something as simple as, like, okay, I might just need to re-implement a model and a training process, or maybe just the model. I might need to I might need to re-implement just the model in Rust for the ESP32, which basically means I can either use burn. Actually, I have to use burn. I have to use burn. Now, I can use burn. There, my options are, if at all, I'm able to convert this model. Um, Again, I don't know what the situation is going to be. Is it going to be one model, or is it going to be like multiple models together, or like what's going on there? I guess we'll find out once we learn. But dude, I am so excited to learn robotics through this course. I don't. Oh, just a second. I accidentally hit a key. Okay, so you can guess how excited I am. I'm accidentally hitting keys. Okay, so um, I want to get into this course. I don't care if the course isn't complete yet because it's probably going to take me some time to even get through these three chapters, these three what do you even call them? Chapters? Sections? I don't know. But yeah, you know what? Okay, what did they say for what you need? What tools do I need? Um, don't have a robot? No problem. You can follow along with simulated environments and data sets. The concepts translate directly to real hardware when you're ready. Dude, that makes me excited. I'm hope dude, I this stream wasn't even supposed to be about robotics, but I suddenly remembered this robotics thing. And because I'm excited about this robotics thing, I'm like, hold up, hold up, hold up. Actually, so here's something that I could try to do. Okay. What I want to do is I don't want to train the models in Burn. I want to run inference on the models in Burn. I want to train the models using Python and PyTorch, and then re-implement the model in Burn. I feel like that's going to be a sort of gentle or gentler introduction for me to Burn, because I feel like getting into Burn and having to learn how to build the model and then also learn how to train the model, I feel like that's going to like use up a lot of my time. I mean, it's beneficial info, and eventually I'm planning on learning it anyways. It's not like I'm not planning on learning it, but yeah, if I can stick to just implementing and using the model, as in running inference on the model, so I'll build the model in PyTorch, train the model in PyTorch and Python, export the weights as safe tensors, and then load that safe tensors file into my Rust program where I've redefined this model in Rust using Burn. And then I can run inference on it. I mean, a lazy way out would be to convert that model, the PyTorch model to Onyx, and then use Onyx to Burn to get the Onyx to Burn tool to actually, do the entire conversion for me, which my initial models, I think the operations or the operators that are being used okay, I was about to say that I think the operators that are being used in these models are probably going to be supported by the Onyx to Burn tool, but I don't know that for sure because I don't even know what the operators are. Like I don't even know what kinds of models are going to be used here. I guess we'll find out, right? Learning and assessment. This course is designed for self-paced learning with built-in assessments to help you track your progress. All right. Then, no formal certification required. The goal is to gain practical knowledge and skills in robotics that you can apply to your own projects and research. And that is exactly what I want to do. Keeping that in mind, I'm wondering if it's time for me to start learning Burn because I did actually start learning Burn, but then I kind of pushed it to the side. I did start learning Burn though. I got up to the point where like I installed the library, I loaded the thing up, I loaded up my project. Burn does take or Burn does cause the Rust analyzer to take a significant amount of memory. Fortunately, I had that much lying around, so that wasn't an issue. Where was I going with this? Yeah. Then I did some very basic stuff like defining tensors and doing like one or two operations with those tensors. I think maybe we touched on on defining a neural network as well. I didn't really go deep enough into it that we would get to the training loop. Because, dude, I feel like I need to do this a couple of times in PyTorch to understand the training loop. Because I haven't fully, like, I don't like remember all of the steps, and I don't want to memorize that process. I want to understand the process. I want to understand the steps that I need to take so that I'm not memorizing things. It shouldn't be like, oh, okay, there's this checklist of things that I have to do, and I have to remember this entire checklist. Have I done this? Have I done that and that and that? No, I don't want it to be like that because I hate having to memorize things. I prefer to understand things because that way I actually remember them. And of course, understanding is much better than just mugging it up. Um, what was I saying? What was I saying? Understanding is better than just mugging it up. But where was I going with that? Oh, yeah. So I don't want to just I don't want to just memorize stuff. I want to understand that, hey, when I'm trying to achieve this, when I'm trying to accomplish so and so task, or perform so and so task, within this task there are multiple smaller tasks that need to be done in order for this task to be complete. So I need to understand all of those different things that need to be done in order to actually finish the task, which in this case is training the model. Because there's a bunch of like different things that you would have to kind of like remember initially. There's the whole thing of like, okay, how are we loading a data set? Once a data set is loaded, um, how are we splitting it? How are we pulling data out of the data set? In PyTorch, you have something called data loaders and data something else. I forgot. One is for like loading the data set, and the other is for, I think the other one I think the other one was for iterating over the data set. I don't remember. Hold on. Let me look up the example again. PyTorch learn. I need to go to the very basic PyTorch. Okay, learn the basics. There you go. Beginner basics intro. There was data loader. Oh, there was data sets and data loaders. So data sets is for downloading the data set, but that data set is downloaded as some sort of like, it's a separate object kind of thing. And then you use data loaders, which I think the data set API is downloading data loaders, and then you use those data loaders to actually load the data. There's various like functions that help you split the thing into, you know, labels and values, and split it into training and test splits and all of that good stuff. So initially there's some of this stuff that you have to kind of remember, right? Then there's the actual like defining of the neural network, which that I actually do remember it because I've understood that process. I've understood what exactly I need to do. And so it's less about memorizing and more about like, hey, okay, I'm doing this and this and this, and there's a reason why I'm doing all of this stuff. That is why I remember it. Then comes the training process, which I have not spent nearly enough time working on. I've only set it up like once or twice, and so I need to set the thing up myself a couple of times so that I'll actually remember the thing. So maybe I shouldn't be touching Burn right now. Maybe I should just stick to the Python side. Once I have properly understood the entire process, which I understand the process. It's just like once I remember the entire process, then I'll know that okay, in Burn also I have to do something similar. Um, I want to try to at least do like, you know, basic training in Burn, but the main objective in Burn is not to train the model, it's to run the model because the objective with Burn is to um, export this model. No, well, not export the model. Export this binary and um, run it on an ESP32. the whole idea behind using burn at all in this case is not just to, have the model running in Rust. Having it running in Rust is great. There would definitely be benefits of that as well. I'm sure burn is going to apply a ton of optimizations depending on what backend you are using. So if I'm doing like the if I'm doing a backend that runs on like a PC, then there's going to be a ton of optimizations in there. Additionally, because of WGPU, I might actually be able to use the GPU, the iGPU of my CPU to do some of the calculations. I'm not entirely very optimistic about that because whether these iGPUs are able to do compute operations really depends on the generation, because the older ones, like the older, like in terms of the age of the CPU or the generation of the CPU, when you are going down that list, the older the generation is, the less capable that GPU is of doing compute operations. It can do like graphics stuff, but specifically compute operations. The older generations, as you go older, they start to get lesser and lesser capable. And I have a couple of different processors here, fortunately. One of them, I actually had like a comparison that I had done. I forgot where exactly I had done that comparison. Okay, so I have four desktops in front of me right now, right? And one of them is incredibly old. It is using it's using a dual core processor. Like that's how old it is. And it's using 2 GB of DDR2 RAM. So like I'm not even planning on doing it. 2 GB, 1 GB, 2 GB, 2 GB of DDR2 RAM. So I'm not even planning on, doing anything with that. I'm using that for a different purpose. Then I have two laptops and one desktop. And they each, like in their age, you have one which has a newer processor, one that has a much older processor, and then one that has an even older processor. So in terms of getting, good mileage out of, or getting them to do these calculations on the GPU, on the iGPU, not just the GPU, the chances they become lower and lower. However, it is also worth mentioning one of the newer machines that I have, newer, well, compared to the other two, that machine does also have a NVIDIA GPU. That laptop does also have an NVIDIA GPU. And then one of the other laptops, which is older than this laptop, it has an AMD GPU. So if WGPU, which is a Rust crate for web GPU related things, if WGPU is able to handle the abstraction for both of these, the NVIDIA GPU and that AMD GPU that I have, then we're probably not even going to be using the iGPU. But then the desktop doesn't have a discrete GPU. It only has the processor and the processor's iGPU. Either way, okay. Anyways, the whole point of using burn is, at least right now, is not to run these models on on the PC. It's to be able to run these models the on the ESP32. I forgot why I was talking about this, so we're going to continue with this. Okay, recommended approach. Take your time with each concept. Robotics builds on foundational understanding. Try the code examples. Hands-on experience reinforces learning. Take the quizzes. They help identify areas that need more review. Take breaks between units. Unit, that's what this is called. Okay. Yeah, take breaks between units to let concepts sink in. How to get the most out of the course. To get the most out of this robotics course, we recommend engage with the community. Join the discussion here. Is this leading to Discord? No, there's a discussions thing in Spaces. Okay, good. Explore LeRoBot documentation and connect with other learners interested in robotics. Practice with code examples. The best way to understand robotics is through hands-on experience and with real data sets and algorithms. Then take the quizzes seriously. They're designed to reinforce key concepts and identify areas where you might need additional review. Explore beyond the course. Try LeRobot examples, experiment with different data sets, and see how the concepts apply to your own interests. Then we have the acknowledgements. Awesome, great. Okay, let's you know what? Let's jump into this. Let's jump into this. How long into the stream are we? I think half an hour into the stream, I started talking about LeRobot, right? Maybe I'll rename the stream and say, yeah, we are getting into robotics. Okay, getting started with LeRobot. Throughout this course, that is not easy to say, LeRobot. How? Let's say LR. Okay, throughout this course, we'll use L. I'm just going to say LeRobot because it doesn't flow off the tongue that easily. But like, I'm also not going to remember LR. I'm going to say LR. Okay. Throughout this course, we'll use LR, Hugging Face's comprehensive open source robotics library that democratizes access to state-of-the-art robot learning techniques. LR addresses. I'm just going to say LeRobot, dude, because then otherwise I'm having to stop to think that hey, it's not LeRobot, it's LR. LeRoBot addresses one of the biggest barriers in robotics education and research, the complexity of working with real robotic systems and data. Okay. The library provides intuitive dataset handling that makes, oh God, dude, I'm hitting keys that I'm not supposed to be hitting. Okay. The library provides intuitive dataset handling that makes working with complex robotics data as straightforward as working with text or images in traditional machine learning. You'll you'll have access to pre-trained models that serve as strong starting points for your own projects, allowing you to build upon proven algorithms rather than starting from scratch. LeRobot also supports deployment on real robotic hardware, bridging the gap between simulation and real-world applications. Perhaps most importantly, it connects you to a growing community of robot learning practitioners, from researchers at leading institutions to hobbyists building amazing projects at home. Hell yeah. Okay, installation preview. We'll walk through the installation. We'll walk through installing LeRobot in Unit 2, but if you're eager to get started, then this. Okay. Uh, you know what? Hold on. We're gonna do something here. CD snuts. CD make der learning LeRobot. Then CD learning LeRobot. Um, hold on. Yeah. Uh, let's say LR proj O1. Okay, here we need VNV, ENV, 3.14. Okay, that's done. Source, ENV, bin, activate. Then UV pip install LeRobot. Backup. backup. I just activated, wait, okay, I activated this, right? Let me do which Python. Okay, all right. Let's just to be safe. Let's do that. And now let's install. Let's see how big it is to install. In the meantime, let's move on to the next thing. So, ready to um, ready to start your robot learning. Hold on, dude. This is taking some time to download. This is definitely not taking time to install. This is taking time to download, I believe, or it's searching for something. Yeah, I think this is taking time to download. Well, anyways, ready to start your robot learning journey? Let's begin with understanding why classical robotics approaches have limitations and how learning can help overcome them. Introduction to robot learning. Hold on just a second. Are we dropping frames? Because I just had something happen on another thing. I think we might be dropping frames. There it is. Okay. It was a little hiccup because of internet problems. And this is downloading. Oh God, this is downloading everything that it needs. This is oh shit. This is downloading. Oh my God. This is downloading a whole bunch of CUDA related stuff, I believe. Why does it require CUDA? Is there no way for me to do like um, I mean, I'll let the download go right now, but holy shit. Is there no way to do CUDA or do the robotics stuff, LeRoBot stuff without CUDA? There has to be like some flags that I can provide that make it so CUDA is not being used because I'm not going to be using CUDA here. Well, anyways, I mean the download has started. Might as well just let the thing finish. These are massive downloads, dude. But yeah, usually when you install PyTorch with CUDA support, then it is pretty big. Uh yeah. Wait, okay. Um Let me try asking Gemini. Maybe I can just stop this. I'll remake the entire environment. I mean, to be fair, the thing is downloading pretty damn fast right now. And it's not like I'm losing a whole lot of data because I'm currently on in the free data window of my, day. Okay, I'm installing LeRoBot. It seems to also be installing some CUDA stuff, which I'm assuming is related to um, which I'm assuming is related to. Wait, give me a second here. Wait, what just happened? You're joking. Did that just crash? I think that just crashed. Yeah, I think that just crashed. That is crazy. Did I fill up something or did my memory fill up? Give me a second here. I think that crashed. I'm not sure why it crashed. Let me create a new thing here. Let's cd into this and learning LeRoBot and this and source env bin activate. Before I continue, actually, I think I want to delete this entire environment. Let's recreate the environment and yeah, let's do that and uv vnv p 3.14 env. That's done, and now we activate. Okay. All right. So it seems to be installing some CUDA stuff, which I'm assuming is related to Torch. The thing is, I don't plan on using any CUDA stuff at all. Um, Installing the CUDA stuff is making the download and install, hold on, install unnecessarily long. Let's see if Gemini has some information. I completely understand the frustration. CUDA packages are massive, and if you're planning to run LeRoBot on a Mac, a CPU-only machine, or an AMD GPU, downloading gigabytes of NVIDIA drivers and kernels feels like a total waste of time and disk space. The reason this is happening is that LeRoBot lists Torch as a dependency. By default, most package managers like pip will fetch the version of PyTorch compiled with CUDA. Oh, so I need to install PyTorch myself? Okay, if you haven't finished the installation or don't mind starting over in your environment, the most effective way is to install the CPU-only version of PyTorch before you install LeRoBot. Okay, I can do that. Yes, I can do that. Let's go to getting started, and under getting started, there's the installation instructions. I think so. Yeah, yeah. So I'm doing CPU only, and I'm gonna copy this. This runs on Python 3.10 or later. It did mention something about the latest, like the absolute latest. Okay, Python 3.10 to Python 3.14 is generally installed by default on any of our supported Linux distributions, which means so and so. If you want to install for another version, there are multiple ways. Yeah, okay, I'm doing it for 3.14 anyways. So paste uv pip install. Yeah. So let that install. Okay, it should have like a cached version. There it is. Okay. So PyTorch is installed. Now, um, give me a second here. Just gonna open up my stream. Okay. Um, so we were doing uv pip install LeRoBot. Did Gemini also mention something else? Using environment variables. If you are using a specialized setup or want to ensure the installer doesn't try to upgrade you back to a CUDA version, you can sometimes force the platform. However, the manual pre-install method 1 is usually the most bulletproof way to handle Torch. Why this matters for LeRoBot? LeRoBot is designed to be accessible, and it actually runs quite well on non-CUDA hardware for certain tasks, such as inference. Running pre-trained models on a CPU or Apple Silicon is very feasible. Data visualization, if you are just using it to record data sets or visualize teleportation, you definitely don't need CUDA. Training, this is the only place you'll feel the sting. Training even small ACT or diffusion policies, I have no idea what either of those mean, on a CPU will be significantly slower than on a GPU. That makes sense. Quick verification. I don't think I need to worry about any of that. Okay, so now let's try installing LeRoBot. I hope it doesn't start downloading the CUDA stuff. It says that it resolved 95 packages. Let's just wait. Oh, actually, in the meantime, we can continue reading this thing, right? Why am I waiting? So, robotics. No, introduction to robot learning. Robot learning starts with a simple idea: teach robots to improve from data and experience instead of hand coding every behavior. In practice, this means using examples such as videos, sensor data, demonstrations, etc., and feedback to help a robot get better at tasks like picking, placing, pushing, or walking. Okay, why now? Two trends make this possible. Modern machine learning is increasingly good at finding intricate. Give me a second. Oh, wait. What is. Hold on. What is happening? Why am I hearing my fans? Okay, so there's some kind of compilation going on, which is part of this installation process. I'm guessing the same thing happened during that CUDA thing, but when I tried to run the compilation on the CUDA stuff, everything kind of just crashed because I think there was maybe an or some other reason. But like usually the entire shell only crashes when there's an as in an out of memory issue. Okay, all right, okay. Let's just keep an eye on this. In the meantime, I can keep reading. I don't know if the sound of the fan, the sound of the fan is coming through on the mic, but like as in is it being picked up by the mic? I don't know, but like it's getting louder. I think you guys might be able to see the numbers. You can see the temperature of the CPU or each of the cores. It's slowly getting up to close to 80 degrees. Okay, this is getting louder. This is getting louder. Give me a second. I need to reduce the load on. Oh God. Okay. Just a second. I need to crash something here. I'm gonna I'm gonna close this. I'm gonna crash OBS. Well, stop OBS and close OBS, and also turn off the SRS, the RTMP server, just to put lesser load on the machine. So we are good in terms of. Wait, why is it taking so long? Is it still doing the CUDA thing? Okay, I think we are okay. Okay, it reduced. It reduced down to 1 and we are good. Okay, all right. Much better. And everything is installed. The package Hugging Face Hub does not have an extra named HF transfer. The package Hugging Face Hub does not have an extra named CLI. Okay, I'm gonna restart the entire thing. Um, okay, so let's run that. Oh, my browser also crashed. So there was definitely an that happened. That's okay. That's okay. Right. Give me a second while I start all this stuff back up. Okay, so I have the RTMP server running. I now need to start up OBS, but before that I need to wait for Firefox to open up, and then I need to do the whole like resume thing. Man, that's crazy. Like just like that, the memory spiked and everything crashed. I'm glad that it crashed these specific things rather than freezing the entire system. I'm super happy about that. I'm never going to complain about that because I have an entire I have like an entire tmux server running on this machine. I cannot afford to have this machine crash. This machine is hosting 4 or 5 different tmux sessions, two of which I'm looking at on stream actively. Right now you guys can only see one, but the other one I'm going to bring up once I start up OBS. Give me a second. I'm just doing that. Okay, this is started up. And we do that and we start streaming. This is running. We have opened that up. Okay, and I think we should be able to start up the Python thing again. Was it here? No. Was it here? Yeah. Right, so let's open that up and hopefully OBS picks it up automatically. Yes, it did. Great. Awesome. So we are good to go. If you look here, hold on. Yeah, if you look here, all of this stuff has been installed. A bunch of, I'm assuming, Hugging Face stuff has also been installed. And then, of course, there's Torch and various things that come along with Torch. That's also been installed. Let's see if we can get like a size for this. I think it was this. 1.7 GB. That's how big this entire environment is now. 1.7 GB. This is without the CUDA stuff, fortunately. This is without the CUDA stuff. Now, what was I going to do? I was reading this, right? Actually, I'm curious about something. Let's open up this, and I want to see how much memory usage this thing will have. Let's create a new, so pi01.py. Okay. All right. Now let's come here and see how much memory. Give me a second. Memory. Yeah. I'm not expecting it to take like a crazy amount of memory, but like considering that the package itself is, you know, that big. Okay, let's try that. Okay, and now let's see if any of the node things start to take up more memory. Well, I can come back and check on it. Right, so let's continue reading. Why now? Two trends make this possible. Modern machine learning is increasingly good at finding intricate patterns, and robotics data sets are becoming easier to collect and share. Together, they let us move from classical, write the physics and the controller approaches to learning based methods that adapt from data. Okay, for example, a robot arm can learn to grasp a block by trying actions and getting rewards for progress, which is reinforcement learning, or even by watching and imitating human demonstrations, which is imitation learning. Okay. Over time, the same ideas scale to many tasks and even different robot bodies. By the end of this unit, you will understand in plain terms what robot learning means and why it's useful. See concrete examples of learning from demonstrations and from trial and error, and you will know what we'll build towards in the next units and how LeRoBot fits in. Okay, some history. Robotics is about helping humans with repetitive, tiring, and dangerous tasks. People have been working on this challenge since the 1950s. Recently, advances in machine learning have opened up new ways to build robots. Instead of requiring human experts to write detailed instructions and models for every task, we can now use large amounts of data and computation to help robots learn behaviors on their own. Something that I'm noticing these days, the more I explore a bunch of these different models, something that I'm noticing is that an increasing trend is not to train a model from scratch, but rather use a pre-trained model and then on fine tune it for a specific task. Because when you pre-train a model, you are not pre-training it. Whoever pre-trained the model, they have pre-trained it on massive amounts of data, and that massive amount of data, it gives the model whatever base foundational knowledge it needs, and then you can build up on that foundational knowledge uh, through fine tuning. The advantage for you and the benefit for you in this case is that you don't have to use massive amounts of computing or computational power. You don't have to use massive amounts of compute to train the model from scratch, because that would be incredibly expensive for you. Instead, you would still probably have to use massive amounts of computing, but not nearly as massive. You would have to use a certain amount of computational power to fine tune a model and build upon what the model is already capable of doing. Yeah, that's what I was trying to say. That this is something that I'm noticing more and more, where these models are being trained on some base knowledge, some foundational knowledge, and then you fine tune these models to do specific tasks for you. And this ends up being a much better alternative to training an entire model from scratch completely, because you just cannot do that unless you have massive amounts of computing power. Um, and that would be incredibly expensive to do as well. And the fact that we are getting these models for free is amazing. The fact that a lot of these companies are aiding AI research by training these models from scratch and providing us with like a base foundational model that we can build upon, that is amazing. That is actually helping the community further do AI research, because people who don't have massive amounts of computing power, they're still able to build upon these models and continue doing their research. And I'm guessing research then continues in this direction with this practice of like, okay, we are going to use this base foundational model and we're going to build upon it, rather than, the practice of training something from scratch. And I'm not entirely sure where the practice was first like adopted from, but like the first place where I saw it was with LLMs, because like LLMs are also trained on massive amounts of data. Well, LLMs and even generative AI, but I think LLMs did it first, not Gen AI. I could be wrong about that, because even Gen AI models for image, for example, even they were trained on like massive amounts of data, right? Forget about like the main issue is not like how you're going to store that data set. The main issue is how you're going to train such a very complex model on this massive amount of data. You need crazy amount of computing power to be able to do that. Anyways, some history. Robotics is about. Wait, I think I read that already. Recent advances, so and so, so and so, so and so. Okay, detailed instructions for every task. Okay, we can now use large amounts of data and computation to help robots learn behaviors on their own. Some context. The 1950s saw the birth of both artificial intelligence and robotics as distinct fields. The first robot ever was Unimate. Hold on. Let's go down. I was about to say memory lane, but like it's not my memory. I wasn't alive during this time. Um, let's go check out history. So, okay, the first robot ever was Unimate, invented in 1961. It's taken nearly 70 years for these fields to converge in meaningful ways through robot learning. I'm assuming they mean by these fields, they mean robotics and artificial intelligence. Oh, yeah, okay, okay, yeah, it said that in the very first sentence. The 1950s saw the birth of both artificial intelligence and robotics as distinct fields, and it took nearly 70 years. Okay, that's crazy. Well, yeah, 1950s, right? And now we are in like the the 2020s, basically. Like, we are in 2026, so 2020s. Uh, where was I? To converge, okay, to converge in meaningful ways through robot learning. The future of robotics. Today's robotics researchers are moving away from the traditional approach of writing detailed models and control systems. Instead, they are embracing machine learning. They're embracing machine learning to create robots that can learn direct connections from what they see to what they do without needing separate systems for perception and control. They can also extract useful information from many types of sensors such as cameras, touch sensors, microphones, etc., using data-driven methods. They can also work efficiently, they can work effectively without needing perfect models of how the world behaves. They can take advantage of the growing number of open robotics data sets that anyone can access and learn from, and they can work effectively without needing perfect models of how the world behaves. You can watch this video to get a better sense of the paradigm shift currently undergoing robotics. Where is this leading? Uh, I'll look at this later. I'll look at this off stream. Um, this is Unimate. Unimate was the first industrial robot which worked on a General Motors assembly line at the Inland Fisher Guide plant. Okay, why am I paying attention to the names? Okay, whatever plant. In 1961, they were made. In fact, they were in fact a family of robots. Okay, great, awesome. Oh, this is the robot. That's crazy. Hold on. This. Okay, this is real. Usually when I would see something made like this, I would think that they've made something for like movies. Um, but then this is when I think about like, okay, robotics arm from like back in the day, I would think about something like this. To be fair, I'm not getting a good image of what this is, and actually both of these are actually Unimate, which is crazy. So yeah, I'm definitely not getting a proper um, image of this because of the perspective. I'm assuming if I would look at it from like the side, then I would get like a proper like this kind of view. Anyways, it looked like very movie kind of look, because I've seen a lot of movies from back in the day when they try to depict robots, they would create these kinds of shells. Um, Wait, there was a patent around this? Okay, Duvall's earlier methodology involving the conversion of analog information to electrical signals formed the basis of of, of subsequent patents. The patent proposed a cost-effective general-purpose article handling machine for diverse industrial tasks with programmable motions, including gripping mechanism. They patented this. Okay, okay. Anyways, uh, I don't need to pay too much attention to this. Right. Um, Key insight. This shift represents a fundamental change in how we think about robotics, from engineering precise solutions to learning adaptive behaviors from data. This trend is especially important because it mirrors how foundational models like GPT and CLIP were developed. These machine learning or artificial intelligence systems learn to understand and work with text and images by training on massive data sets. As robotics data sets grow larger and robots get equipped with more diverse sensors, regular cameras, infrared cameras, LiDAR, microphones, and so on, applying similar learning approaches to robotics becomes increasingly powerful. Robotics naturally requires expertise in both software and hardware. Adding machine learning to the mix means robotics practitioners need an even broader set of skills, which raises the bar for both research and real world applications. References. For a full list of references, check out this tutorial. Check out the tutorial. So where's this tutorial leading? LeRoBot robot learning tutorial. For a full, okay, what am I looking at right now then? Oh, this is a space. This is a space. Okay. I don't know what all this is going to be loading, and I don't know how heavy it's going to be. So what I'm going to do is close this. This would be interesting to look at. No, you know what? I can open it up, let it load, and then I'll come back to it. In the meantime, I can probably close a couple of other things that might be taking up, you know, memory. Let's close the agents thing. Um, I have distill BERT open. I don't need this. I don't need this. Okay. All right. Okay. Okay. There's a lot of information here, and like code examples and these images and stuff. Okay. All right. Let's close this for now. I'll open this up on another machine where I can have a slightly more smoother experience. For now, let's continue reading. Okay, LeRoBot, an end-to-end robot learning library. Okay, now that we've learned some history, let's explore the main Python library we'll be using throughout this course, LeRoBot. LeRoBot is an open source library for robotics developed by Hugging Face. Think of it as a complete toolkit that handles everything from controlling real robots to training advanced learning algorithms all in one place using PyTorch. I'm glad that it's using PyTorch. What makes LeRobot special is that it's vertically aligned. What does that mean? This means it provides a unified way to work with real robots, handle complex multimodal data like combining camera feeds with sensor readings, and integrates smoothly with the PyTorch and Hugging Face tools you might already know. Essentially, LeRobot aims to be your one-stop library for robot learning projects. Supported robots. LeRobot currently supports accessible platforms such as so and so 3D printable arms. 3D printable, hold on. what are the motors that are driving this? Wait, let me look this up. SO100, okay, SO100 ARM. Is this a link? This is not a link. This is a name. Maybe here there might be links. Imitation learning, cameras, bring your own policies, bring your own hardware. That's what I'm looking for. Okay. Choose your motors. For controlling dynamic Dynamixel servos and VTech servos. I don't have either of the. Actually, I need to check what kind of servo I've got. Follower implementation. Where is no? Hold on, dude. I'm looking at this. There's something called the Robot Studio that made I think they made some kind of standard or some kind of blueprint for designing this. So it's a standard OpenARM 100. I have no idea what that means, but looking at this thing, yes, this can be controlled by. Dude, I need to order one of these for myself. How expensive is this? It looks kind of expensive. I'm seeing what could be control. I should open it up here. Hold on. Um, GitHub, Hugging Face. No, this is not what I'm looking for. For VTech and Dynamixel, we currently support these servos. VTech, so and so, so and so, so and so. Okay, if you're using VTech, I need to look into like which one of these I have because what I have is most definitely like knockoff of whatever the branded stuff is, but like I don't know what it's a knockoff of. It works. Actually, I don't even know if it works because I've never actually tried out those servos or the servo module ever since I got it. I'm just hoping that the thing works. Um, hopefully it works. But yeah, I want to open this thing up for you. Actually, wait, ARM. Okay, let's look this up. Low cost AI ARM Servo Motor Kit Pro. Let me see how much this thing costs. Oh, okay. I cannot afford that. Yep, I cannot afford that. Though I should look up this name and see if I can find cheaper versions. Um, yeah, no, I cannot afford any of these. That sucks. Though this is giving me an idea, I should probably also add some sort of robot arm to my list. Um, a simple robot arm, something that has like a weighted base, that won't very easily tip over, or something that has a base that I can put a weight in. I feel like that's a better way to put it. Something that has a base that I can put a weight in, because I have weights that I can like use to hold the arm down as long as there is a base that I can put something in. Yeah, this is giving me ideas because I have the servo motors. I can look for actually let me look this up. ESP32 robot arm. They are all expensive, dude. Let me look up small robot arm. They're all so expensive, dude. I cannot afford this. No, no, no. I need to find a cheaper way to go about this. I need to find a cheaper way to go about this. Because okay, I have the servo. Actually, I have multiple servos. I have servo modules to control the servos. And I'm also going to have the power. I'm going to be able to power the thing externally. It's not going to be powered through the ESP32. My main issue is the robot arm itself. Basically, any sort of assembly in which I can put the servo motor and control those things. I need the assembly. I don't need the electronic parts. I need the mechanical parts. That's what I'm saying. Um, I need the mechanical parts. Yeah, I'm gonna have to look into this, but I cannot afford any of this. It's not like they're like stupid expensive. I don't want to make it seem like they're like stupid expensive. It's just that they're still expensive. They're still expensive. I cannot afford this. So instead, what I'm going to try and do is try and find a cheaper way to assemble an arm and try to do something with that. Yes, I'm gonna do that. I'm definitely gonna do that. I just got an idea. What if, imagine this, right? Imagine I'm able to get like uh, imagine I'm able to get a sort of arm that I can connect two servo motors to, and both of these arms are like they're connected together through two hinges. Three arms, let's say, connected through two hinges, and the hinges, they have servo motors, and then I can try and make this thing move around. I'm getting some ideas here, dude. Okay, you know what? Yes, I'm glad that I'm thinking about this because this makes it so I'm not limited to just what they are teaching. So I'm not limited to just this robotics arm thing. I can probably apply this knowledge to the the things that I am able to build. Like for example, I have like a small like robotics car kind of thing. I forgot what it's called. It's like a self tracking car or something like that. It comes with DC motors and stuff. There isn't necessarily servo motors involved, but I can make it work. I can make it work. I need to look into the specific arms that I can get that I can use my servo motors with. I need to look into that. Yeah. Okay. Anyways, let's continue reading this thing. Okay, one key advantage is that LeRoBot uses a standardized approach to connecting to different robot platforms. This means adding support for new robot for new this means adding support for new robots requires much less work than starting from scratch. All right. The library also introduces LeRoBot Dataset, a specialized format for robotics data that the open source community is already using to share datasets efficiently. LeRobot includes implementations of many cutting edge robot learning algorithms, all built with PyTorch for efficiency. It allows it also provides tools for running experiments and tracking results. Perhaps most importantly for real-world applications, LeRobot separates the thinking part, which is planning what to do, from from the doing part, which is the execution actions. This separation is crucial because it allows robots to react quickly and adapt better when things don't go as planned. Performance note: LeRobot's optimized inference stack is crucial for real-time robot control, where delays of even milliseconds can affect performance. This separation of planning and execution is a key innovation. Then we have references. Okay. Robotics transformer for real world control at scale. All right, okay. Then let's move on to LeRoBot dataset. Okay, LeRoBot dataset is a standardized dataset format designed to address the specific needs of robot learning research. In the next few minutes, you'll see what problems it solves, how it's organized, and to look where to look first when loading data. The format provides unified, convenient access to robotics data across modalities, including sensory motor, sensory motor readings, multiple camera feeds, and teleportation status. Okay, LeRoBot dataset also stores general information about the data being collected, including textual task descriptions, the type of robot used, and measurement specifics such as frames per second for both image and robot state streams, together with the types of cameras used, their resolution and frame rate. Why a specialized format? Traditional ML datasets like ImageNet are simple one image, one label robotics data. What? Are simple one image, one label. Robotics data is much more complex. It's multimodal, images plus sensor readings plus actions all synchronized, temporal, both observations and actions are recorded over time and very much in a sequential manner. Episodic, data is organized in trajectories slash episodes, and high dimensional, multiple camera views, i.e., multiple images, joint states, forces, etc. LeRobot dataset handles all this complexity seamlessly. LeRobot dataset provides a unified interface for handling multimodal time series data and integrates seamlessly with the PyTorch and Hugging Face ecosystems. It is, it is extensible and customizable and already supports openly available data across a variety of um, embodiments in LeRobot. Hold on. It is extensive. Oh, in LeRoBot, we are talking about the LeRoBot dataset. In LeRoBot, ranging from manipulator platforms like so and so to humanoid arms and hands. Uh, to humanoid arms and hands, simulation based datasets, and even autonomous driving. The format is built to be efficient for training and flexible enough to accommodate diverse data types while promoting reproducibility and ease of use. Okay, all right. Okay, so here's an example. We have tabular data, we have visual data, and we have metadata. And an example draw from LeRobot dataset. So we have the image and then all of the data with it. Okay, the dataset class design. You can read more about the design choices behind the design of our dataset class here. A core design choice behind LeRobot dataset is separating the underlying data storage from the user-facing API. This allows for efficient storage while presenting the data in an intuitive, ready-to-use format. Think of it as two layers, a compact on-disk layout for speed and scale, and a clean Python interface that yields ready to train tensors. Datasets are always organized into three main components: tabular data, visual data, and metadata. Okay, all right, cool. As you browse a dataset on disk, keep these three buckets in mind. They explain almost everything you'll see. For scalability, should I read all three of these? Okay, tabular data is low dimensional, high frequency data, such as joint states and actions stored in efficient memory mapped files and typically offloaded to the more mature datasets library by Hugging Face, providing fast and limited memory consumption. Okay, visual data. To handle large volumes of camera data, frames are concatenated and encoded into MP4 files. Frames from the same episode are always grouped together into the same video, and multiple videos are grouped together by camera. To reduce the stress on the file system, groups of videos for the same camera are also broken into multiple subdirectories. Then metadata. A collection of JSON files which describes the dataset's structure in terms of its metadata, serving as the relational counterpart to both the tabular and visual dimensions of data. Metadata include the different feature schema, frame rates, normalization normalization statistics, and episode boundaries. Hey, give me a second here. I just need to do something. Okay. All right. As you browse so and so, right. For scalability and to support datasets with potentially millions of trajectories hundreds of resulting in hundreds of millions or billions of individual camera frames, we merge data from different episodes into the same high-level structure. Concretely, a single data file stored with a parakeet file, no, with a parquet file. I need to look into what that means. Or recording stored in MP4 format often contains multiple episodes. What what is an episode here? Episode. Okay, I can look into what an episode is later on. This limits the number of files and speeds up I/O. The trade-off is that metadata becomes the map that tells you where each episode begins and ends. In turn, metadata have a much more relational function, similar to how way in a relational database, similar to how in a relational database, shared keys allow to retrieve information from multiple tables. An example structure for a given LeRoBot dataset would appear as so and so. Okay, I don't think I need to understand what an episode is, but I'll look into that later. All right, reading guide. Start with so and so to understand the schema and FPS, then inspect stats for normalization. Finally, peek at one file in data and videos to connect the dots. Storage efficiency. By concatenating episodes into larger files, LeRoBot dataset avoids the small files problem that can slow down file systems. A dataset with 1 million episodes might have hundreds of actual files on disk. Pro tip, the metadata acts like a database index, allowing fast access to specific episodes without loading entire video files. Each time they are giving, oh, they're all linking to the same tutorial. Okay. Then code example. See, I'm kind of confused about where we are right now in this. Also, I think my system is getting stuck. I think my system is getting stuck. Where are we right now? Oh, we are here. All right. There it is. Okay, cool. Code example, datasets in practice. And then we have classical robotics, which expands like this. Okay. All right. Yeah, I think I need to look at that tutorial that they've linked. Maybe there's like a bunch of important information in there. I was assuming that I'll get all of the important information from these, like, you know, um, chapters here, but like, I guess not. This section shows you how. Well, okay, no, that's not fair to say. I was hoping I would get all of the information from here, but I guess it's kind of divided amongst the two. Or maybe that tutorial space is like one central location for all of the information that we are getting from all of these different chapters. Okay, we'll start with. Okay, this section shows you how to work with robotics datasets from Hugging Face using LeRoBot dataset class. We'll start with simple examples and gradually add complexity so you can copy and adapt the approach that best fits your project. The key thing to understand is that any dataset on the hub that follows LeRoBot's format, okay, I think I'm going to need to spend some time learning how to use LeRobot dataset. Um, yeah, I'm going to have to spend some time learning how to use the LeRobot dataset class because it seems important in order to be able to in order to be able to load the data that I'm going to be using throughout this entire course. This is kind of reminding me of how I had to learn the PyTorch datasets thing in order to, be able to load up datasets and use them for training and inference. And also in Hugging Face, I would have to learn how to use the datasets, which the datasets library in Hugging Face is actually surprisingly simple. They've made it to not be convoluted at all, yet I think it can still do complex stuff if you need it to. However, it's built to be as simple as possible to use, which is great. So, like, it wasn't really a huge issue diving into it. But yeah, okay. So, um, I need to spend some time learning how to use this data set. I think I should do this off stream. Let's move on to the next chapter, assuming I've finished this chapter. Okay, let's see what more. Wait, what are these checkbox type things? Oh, is this a quiz? This is a quiz. Okay, okay. I'll come back to this. I'll come back to this. Wait, I'm not signed in. I can't complete the quiz anyways. Yeah, never mind. Introduction to classical robotics. In this section, we'll build a foundation in classical robotics that'll help you understand why learning-based methods are so powerful. We'll start by exploring how robots generate motion, look at common types of robot movements, and work through a concrete example before discussing the limitations modern that motivate modern approaches. Okay, key takeaway. Learning-based approaches to robotics address fundamental challenges that traditional methods struggle with. Modern robotics needs methods that can work across different tasks and robot types, allowing one approach to work effectively in many situations rather than requiring custom solutions for each problem. We also need to reduce our dependency on human experts who manually design rules and models for every situation. Finally, The field needs approaches that can take advantage of the rapidly growing collection of robotics data sets, learning from the collective knowledge captured in these large scale data collections. Okay, different approaches to robot motion. Dude, hold on. I am crazy excited about this. Okay? I'm I cannot I cannot I cannot put into words how excited I am to learn all of this stuff and to eventually connect this to my ESP32, electronics projects stuff. Um, I need to kind of figure out where I want to go, how I want to divide my time, because there's a couple of things I need to be focusing on right now. Okay, let's open up this courses to learn, temp, current focus. Now there's going to be a current focus 03. Current focus 03. Okay, in current focus 03, deep learning, actually FCNN, further studies. I want to be a little more specific than just, deep learning. Then, I don't think I need to learn specifically about the Transformers library because I'm using the Transformers library already and doing various tasks with the Transformers library. I'm kind of already learning how to use it, right? We do need to do that LLM course. Okay, I need to continue working on my auto clipper. ESP32 Rust, 100%. I need to move forward with that as well. The only downside here is that keeping all of this in mind, Kaggle and Kaggle data science stuff kind of gets left out, and I don't want to leave that out. I do want to continue with the Kaggle data science stuff. Now, robotics. So HF, robotics course. Is that what it's called? Robotics course? Yeah, it's called robotics course. And we can move this up. This is our current list. The other list, oh, I can remove a couple of things. I can remove this later on when I need to get into it. I'll get into it. I need to get back to Zola as well. I don't know when that's going to happen. Stream AI voice app. I need to get back to that. Onyx. I will get back to that. Like as I'm accomplishing various other tasks, I'm kind of already. I don't even need to get back to it, quote unquote. It's more like, hey, like just learn to use Onyx. That's it. HF transformers, I'm already doing that. Content clipping bot. What did I write here? Yeah, this is what I'm currently working on. The content clipping bot. VTuber app, data science, deep learning. We can get rid of that, get rid of that. Live VFX. I do want to work on this. I do still want to work on the live VFX app. I'm still going to be learning nano stuff. So I'm going to keep all of this. This Tokyo task scheduler, I need to kind of like finish learning the basics of this because I do have something that I need to set up on two systems actually for two separate things, for two separate goals. I need to set up. I need to set some stuff up here. I'm wondering if tomorrow's stream should be more of the robotics course because there's a bunch of stuff here to read, and so it can either be the robotics course or, well, it'll be the robotics course, but in the robotics course, it can either be LeRoBot dataset, like we're learning how to use LeRoBot dataset, or we can continue reading about this classical robotics stuff. The other chapter is not ready yet, which goes into, I believe, reinforcement learning. From let's look at the last chapter in this unit, which is taking some time to load. So I think my system is about to freeze pretty soon as well. Give me a second here. Okay. I also wait. Okay. Yeah. Let's the learning revolution. Okay. Okay. What comes next? This is where they talk about the next things that we're going to be using. I wonder if they okay, you're now ready for so and so. Okay, so and so coming soon. These advanced units will build directly on the foundations you've just mastered. We are going to master the foundations, dude. I wonder if dude, in each of these previous chapters this tutorial has been mentioned. And it's the exact same tutorial because it's leading to this one space, LeRoBot slash robot learning tutorial. I wonder if I should open up that space and just go through that entire thing. And that way also we'll get to learn a bunch of things because I believe there's a bunch of like code examples in there. And not just for LeRoBot. I'm wondering if there's any code stuff being taught here. There's math stuff that it's going into. Okay. Okay. Yeah, I feel like wait, chapter 4 provides an in-depth treatment of forward kinematics, modern robotics. For a full list of references, check the tutorial. Yeah, okay, I think it might okay, wait, let's see if we are able to find some let's let this thing load. Give it a couple of seconds while it does its thing. Okay, here we have a table of contents thing, which is interesting because I've seen very few spaces that actually have like a table of contents thing. So that's pretty cool. Introduction, LeRoBot dataset, code example, batching a streaming dataset, collecting data, okay. Example, planar manipulation, explicit and implicit methods, different types of motion, reinforcement. Wait, they've already written out the tutorial here? Hold on, we can then continue from here. Dude, there's like, this is a whole ass like treasure trove of information. This is one massive, like, look at this. Look at how long the thing scrolls. The thing just keeps going. Look at this. This is one massive tutorial. This is massive. Okay, dude, I think once even after we get done reading all of that extra information through the chapters, I think we can just go through this entire thing. In fact, I'm wondering if we should just go through this tutorial alone and not bother reading the other stuff because the other stuff might also be included in this tutorial. I'm wondering if that's the case. Okay, section classical reviews classical robot foundations. Section learning RL elaborates on the limitations of dynamics based methods, and introduce RL as a practical approach to solve robotics problems, considering its upsides and potential limitations. Learning imitation further describes robot learning techniques that aim to solve single tasks learning, leveraging BC techniques to autonomously reproduce specific expert demonstrations, and then Learning Foundation presents recent contributions on developing generalist models for robotics applications by learning from large corpora of multitask, multi-robot data. Sorry, I was zoning out while reading that because I was thinking about something else. Another thought just came into my mind. Okay, so this is the data sets thing. Okay, then this is okay, all right, okay, okay, all right. Right, so this is the arm that I was looking at, and this is where each of the servo motors go in, um, and like they control, like, how they control the you control the angle of these motors, and through that you control the entire arm itself. Okay, all right. Okay, this is interesting. So this is going into like the math of all of it. Limitations of dynamics-based robotics. All right. Reinforcement learning. Approximate the solution, not the problem. TLDR for expensive high fidelity. The need for expensive high fidelity simulators can be obviated. I need to look up what that means. Learning can be obviated learning from real world data using sample efficient algorithms that can safely train directly on hardware. Train directly on hardware? Okay, all right. Robot learning? Okay, okay, all right. I'm trying to find like where exactly we go into. Okay, code example, real world RL. That's what I was looking for. A code example of this. Right. So we do actually go into this kind of stuff, defining the actor. Okay. All right. So they're going to teach us, I guess, okay, this is great because we're going to learn, I'm guessing, reinforcement learning as well. We're going to learn reinforcement learning before we actually practice reinforcement learning. And that's pretty awesome. Robot imitation learning. And then hopefully we are doing this practically as well. This is actually the 3D printed. I don't know if this specific one is 3D printed or not, but like this was the 3D printed one that we were looking at. Let me, well, we weren't looking at it. I was looking at it on a different machine, and I found out that this is also a little too expensive for me to be able to afford, which sucks. But I need to look for like really small versions because another thing I didn't take into account is depending on the size of the arm, I also need a strong enough servo motor. And I didn't order strong servo motors. I ordered cheap knockoffs and, more importantly, small servo motors. So I need to see how much weight these motors are meant to handle. And then I can buy like something tiny based on that. Like even if I can get like a really tiny arm, hopefully somebody has 3D printed something like that. But yeah, even if I can get a really tiny, lightweight arm that can uh, that I can fit these servo motors into, I would be happy with buying that. I need to see how much it's going to cost though, because yeah, with all the other stuff that I'm going to be buying, I don't think I'll have the money for it. Okay, a concise introduction to generative models. Generative models aim to learn the stochastic process underlying the very generation of the data collected, and typically do so by fitting a probability distribution that approximates the unknown data distribution, P, in keeping with GM literature, P so and so. Okay, this is going to the math of it. All right. We'll get to this. We'll get to this as well eventually. I'm probably not going to be going too deep into the math itself. I'm hoping I'm able to understand the math, at least up until the point where they get to calculus. If it gets to calculus, I'm not sure. And I'm hoping it doesn't get to calculus, because the only problem is that I'm going to have to then go and learn various calculus related principles and stuff. Okay, okay. Where does I'm pretty sure I don't need to do this entire thing. This is just showing what the math looks like. Um, and then we use, the model to actually do the thing. Well, we use the library to load the model to do the thing. Action chunking with transformers. Okay, okay. Yeah, dude, okay. Right. Hold up. Okay, so I think I've rated this person before and they were pretty chill. I don't remember. They seem to be in a meeting right now, um, but I'm gonna raid them anyways. Trying something new, come study with me. This is another person. Though I'm gonna go with this very chill person because even the last time that we were here, they were pretty nice. Um, yeah, yeah. I'm gonna drop into their stream. Their name is Louise McJagger. I remember this name. I remember this name. Okay, so I'm gonna start the raid. And yeah, okay, so that's going to be it for today's stream. I am so excited to get into robotics, dude. I am super excited to get into robotics. Finally, getting into robotics. And I think we are going to focus the next few streams on this. On the side, I'm also going to be actively working on the auto clipper because right now I've already figured out I've already tested the thing out to, you know, get a transcript. I need to find ways to get a transcript with more data than just the text alone. So a transcript with like timestamps and stuff like that would be helpful. And yeah, then once we have that transcript, I can feed that into something and get like a you know um, I'll have to see how to go about using that transcript because the transcript will have like timestamps with multiple. Okay, I shouldn't take too long talking at the outro because the timer for the raid is going to run out. I'm super happy with the constant, streak of streams that we've got going so far. I think we are on a good 10-day streak because I remember I'd streamed on the 3rd of Jan, I believe. Okay, okay. Anyways, I hope you guys have a nice day, and I'll see you all next time. Peace.